So using t results to transform your trig. The advantage of using t results is that it turns your trig integral into something that's just a polynomial or some rational function. And we've got all those techniques for rational functions that we know. So a reminder, if t is tan x on 2, then sine x will be 2t on 1 plus t squared, cos x is 1 minus t squared on 1 plus t squared. If I'm going to use the substitution t is tan x on 2, so that's the substitution we're using, then I'm going to need the t as well. So let's differentiate. The t dx would be a half of sec squared x on 2. Sec squared I'll change to 1 plus tan squared, which is 1 plus t squared. I will turn it upside down because it's going to be easier to substrate in for dx than trying to manipulate it for dt. dx is 2 dt on 1 plus t squared. You'll notice I've boxed those two things. You don't have to go and derive that every time. It's just another t result. In the same way that we just quote sine is 2t on 1 plus t squared, we can just quote dx is 2 dt on 1 plus t squared. That is the t result. So for ones like this, dx on 7 plus 6 cos x. Write down my substitution. I'm going to use t equals tan x on 2, so dx will be 2 dt on 1 plus t squared. Let's substitute in our t results. I've actually substituted in this way. The beautiful thing about these questions is that usually we just use them when we have sines and coses. And the lovely thing about the t results for sine and cos, they have the same denominator. So you're always going to get a situation, fraction on fraction, but the denominators are going to be the same. So you could go straight to that third line, because we know the first thing we're going to do is multiply top and bottom by 1 plus t squared. Just remember to multiply your constant number by 1 plus t squared. And then you go straight to that, and we have a quadratic denominator question. In this case, a very simple one, because we've ended up with an inverse tan there. So we're going to have 2 on root 13, the inverse tan of t on root 13. We're now going to substitute back in for t, and we get this very interesting looking answer of 2 on root 13, the inverse tan of tan x on 2 on root 13, plus a constant. You don't have to use t equals tan x on 2. They're really just half angle results. So if you needed to, you could do the substitution t equals tan x. If you did that, what happens to dx? So going through the same process, the t dx is sec squared, 1 plus tan squared, 1 plus t squared. We end up with dx is dt on 1 plus t squared, rather than 2 dt on 1 plus t squared. In general, this is what will happen. If you let t equal tan x over some constant number, again, there's the process we'd go through, but the coefficient always ends up being, there it is, 1 over a, so when you flip it upside down, you always end up with a on the top. In other words, whatever x is over, then that's what ends up on the top of our dx. 9 times out of 10, or probably more correctly, 9.9999 times out of 10, it's going to be the substitution tan x on 2. But you could use it for other ones if you wanted to. So we'll add those to our exercise there.